In this problem, we're asked to find the third moment of the sum of independent random variables x and y. The density functions are given here as f of x and f of y. So immediately we have two possibilities. We could expand the cubic into x cubed plus 2x squared y plus 2y squared x plus y cubed and find the expectation of all of those things. Or else we could try to deal with x and y together. Now the sum of independent random variables usually leads to convolution, and that could be a long process. However, the sum in special cases satisfies the stability property. In particular, if we added two independent Poisson, we'd get Poisson. If we added two independent normal, we'd get normal. And if we added two independent gamma with the same beta, we would get a gamma with that beta, with a correspondingly different alpha. And so it makes some sense to look at these densities and see if we recognize something. Since they're expressed in terms of this gamma function, one is immediately drawn to see if these are gamma distributed. And indeed, we can see that the first one, x, has this gamma function with 5 over 2. So it could be gamma with alpha is equal to 5 over 2. And we would see from here that the beta would be 2. And then a simple check is yes, this is a alpha is 5 over 2, beta 2, gamma. Similarly, we look at y and we see, oh, the beta here also looks like 2. And when we see inside the gamma function, we see 3 over 2. So y is a 3 over 2, alpha is 3 over 2, beta is 2, gamma. And so we've recognized these densities for x and y. And now we can look at gamma stability. Well, gamma stability says that the sum of two independent gamma random variables with the same beta is again gamma with this beta. So in particular, if x and y are independent, alpha 1 beta gamma and alpha 2 beta gamma, then x plus y is alpha 1 plus alpha 2 beta gamma. So here, beta is 2. So x plus y is gamma distributed with the sum of the alphas, i.e. alpha is 5 over 2 plus 3 over 2, which is 4, and beta is 2. So now we have just one variable here, x plus y, and we just need to find the third moment of that. Moreover, we know it has a gamma distribution. So we can look at the formula for gamma moments, which says the kth moment of a gamma random variable w with parameters alpha and beta is beta to the k gamma of alpha plus k over gamma of alpha. And that's good for any k is equal to 0, 1, 2, 3, 4, 5, etc. So in our case, w is x plus y, k is equal to 3, and alpha is equal to 4. So we can just substitute these in and find that the expected value of our gamma random variable x plus y to the third power, i.e. the third moment, is then beta to the k, 2 to the k, gamma k plus 4 over gamma of alpha, which is gamma of 4. So k is 3, so we have just 2 to the 3, which is 8, times gamma to the k plus 4, k being 3 and 4 being 4 is 7, over gamma to the 4th. And finally, what we can do is recall that gamma is actually a generalized factorial function. So when n is actually, or alpha is actually an integer, we have that gamma to the of n plus 1 is just n factorial. So finally, we have the expected value of x plus y cubed is equal to 8, 6 factorial, because gamma of 7 is 6 factorial, over 3 factorial, because gamma of 4 is 3 factorial, 6 factorial over 3 factorial is 6 times 5 times 4, which is 120. So we have 8 times 120, which is 960.